thank you so much for being with us today. I'm very glad having you here with us. When you want, you can start.
Yeah, exactly. I was just starting the presentation. That was why.
Okay.
Can you see it now?
Yes.
Good. Okay, so what I wanted to talk about here today is learning and reasoning with the trajectory data. So my name is Fredrik Heinz. I'm a professor of computer science here at Linköping University, Sweden. I'm also the professor chair of Sweden, Brazil in AI and autonomy. So I'm also very much looking forward to visiting you. So the plan is to visit you in April next year. So one of my goals there is to build up collaborations between Sweden and Brazil in the areas of AI and autonomy. And I met Flavia. She was here in Sweden earlier this year, so we met in person here, and then we've had some web meetings so far. And now the intention is for me to present some of the research me and my research group is doing. And here I'm focusing more on this learning and reasoning with trajectory data. I also do a lot of work on trustworthy AI. And so my background is that I've been actually quite involved in building autonomous systems for a long time. So we had autonomous helicopters about 20 years ago. I will say a little bit more about those shortly. And today I lead a research group called the Reasoning and Learning Lab. And I'm also very much involved in the university. So I lead the university-wide AI initiatives. I'm also very much involved on the national and international level when it comes to AI-related aspects, including the coordinating a European Research Excellence Center network called Taylor, where we're developing the scientific foundations for trustworthy AI. So I have a pretty broad background and a broad interest. And today I wanted to give, as I said, an overview of some of the main research topics that we are working on in my group. So as I said, we have been working on this collaborative unmanned aircraft systems. Actually, we started in the late 90s and in the early 2000s. We had completely autonomous helicopters. So you can see the helicopter to the right, the one that's white and red one. So these are 100 kilo helicopters that we made completely autonomous and that then can complete or do collaborative missions, both with other UAVs or other robotic systems, but also with humans. So the overall research question we were interested in, we still have some interest in, is this: how do we have a principled approach to building collaborative, intelligent, autonomous systems for complex missions? And actually, the picture here to the right is from an EU project which we were involved in, where we were about building different types of robotic systems to help the human alpine rescuers, both in the winter when people might have got stuck under avalanche, or in the summer when people get lost in the woods or in the mountains, and how to build these kind of systems to support them. So here is a video. Let's see if it works. Oops, sorry, I just took away the sound. So this is a video. I actually don't remember exactly when it's from. It's probably about 15 years old or so. So here we see the helicopter taking off. So everything that you see is autonomous. So of course, takeoff is not that hard. 3D path following. So what we could do here is to, given a 3D model of the environment, generate 3D collision-free paths and then fly these in three-dimensional. So also doing this kind of trajectory following. And we also had special flight mode about vehicle traffic and following. So here the helicopter is controlling itself in order to keep the car in the center of the image. So it's completely controlled based on the car. Then we had what we call push-button missions, which are the missions which only, I mean, there is an operator with a map. The operator selects a number of buildings, and then the system itself plans how to fly and take images of all the different facades and also from above from all of these buildings. So then the whole mission is done completely autonomously. We also have 2 of these helicopters, so they can do joint missions, working together, distributing the tasks between them, and carrying out missions over larger spaces. We also had vision-based landing, so here it can land only based on vision, which means that if we lose the GPS, it can still fly back and then land safely. This is an earlier project we did, I think this is from 2006. And the whole idea here is that we built a control loop between the ground robot and the UAV. So we have a small drone that we built ourselves. And actually the ground robot is from Freiburg. So this was a joint work to be with them. And the whole point here is that the robot is controlling the UAV and using the UAV as an external sensor to, in this case, be able to look on the other side of the obstacle, which the robot itself cannot drive through. So the point here is just to show some of the work that we did quite some time ago. And actually, I think there are some interesting lessons learned from building this. So, of course, the challenges are that we want to support humans and robots, including these legacy systems. We need adjustable autonomy and mixed initiative interaction. We need to manage tasks and information on many abstraction levels. I think this is actually one of the key challenges when you build these very complex systems, is that everything from the kind of low-level control to high-level symbolic planning and reasoning and world modeling and everything in between. You need to be able to coordinate control, reaction, and deliberation. So this is kind of traditional robotics challenges. How do you build these kind of hybrid architectures? But you also need coordination of systems, resources, and platforms. So this is more in the kind of logistics level, how to use your resources in the most efficient manner. And of course, you have very much incomplete information at design time and runtime. And you need to do inspection, monitoring, and diagnosis and recovery on all of these different abstraction levels. So it's quite a complex challenge to do. And this is just to give you a flavor of the kind of platforms we used. And so the ones on the top left are very old platforms, so that we built completely ourselves. And I think we were first with this kind of cage around the UAV in order to protect the users, and you can basically go and push it if you want to. And then we have the Yamaha RMAX helicopter, which we bought, which are then helicopters used for spraying pesticides for the farmers, and that we then turned into a completely autonomous platform. And basically, the control system that we built was flying it as if it was flying with remote control. So we basically kind of interfaced the same way that the remote control would interface with the helicopter. And then we have the quadrotor platform on the bottom, which is a quadrotor platform that we designed from scratch ourselves before the quadrotor platforms kind of became popular. I honestly don't even remember when we started, 2007 maybe, something like that. You can easily, we compare the size to a CD ROM, and I guess those are kind of very antique these days. And there we actually did everything from designing the kind of hardware, but also designing the control electronics to the control boards. And also we can design our own propellers to optimize the kind of trade-off between weight and speed and all these kind of different things. So I think that was a very successful platform. I mean, today we mostly use commercial off-the-shelf platforms like the Matrice platforms and so on. But it's just gives a bit of a background to the work that we're doing today. And one of the main results that we produced was a distributed hybrid deliberative reactive architecture for autonomous systems. So basically, this is the way that we could integrate these different functionalities, doing this control and collecting data and processing it on many different levels of abstraction, and then also doing this kind of monitoring introspection on all these different levels. So I do not intend to go into the details, but this kind of summarizes a lot of the work that we did, and we also wrote a long paper, like 100 pages, describing all the details of the system that we built. So this is the background. So I did my PhD. I was a PhD student during this project. Today, I am part of the Division for Artificial Intelligence and Integrated Computer Systems. So it's one of 5 divisions within the computer science department. And here we have different groups. We have one group working more on knowledge processing and planning and logics. We have a group working on natural language processing. We have a guest professor from Spain, Hector Geffner, who's leading the representation learning and planning lab. So it's very much about the integration of planning and machine learning. And then we have the reasoning and learning lab that I lead. We have a theoretical computer science lab, which is more studying kind of theoretical foundations for, computer science, but also AI. So we're doing a lot of work on constraint satisfaction problems. They've done a lot of work on finding maximal tractable subsets or of the different types of qualitative spatial qualitative reasoning formalisms, such as Allen's interval algebra and RCC8. And then we also have the kind of unmanned aircraft systems part, where they actually build and maintain these autonomous systems themselves. So we have a quite broad division. I actually don't know how many people we are, probably about 10, 20, 30, probably around 30 to 40 people in total, maybe a bit more depending on how you count. So it's moderate, medium-sized research lab. So if we then dive into the work that I'm doing, the reasoning and learning lab. So I have 6 PhD students, 2 postdocs, and a research engineer. And actually now we also have some guest researchers from Brazil. So I have one from USP São Carlos, who's joined us for 10 days ago. I think he joined us. He will be here for a year. So working in a kind of intersection between reinforcement learning, game theory, control theory. And we have a PhD student, Lydia, from UFSCar, who will be joining and working on path planning or motion planning for high velocity UAVs or drones. So we're growing. And actually, one of my students, Matthias Tiga, the one on the top left, he's defending his thesis in 2 weeks. So hopefully he will be a postdoc after Christmas here, but for now he's a student. So our background is very much from a kind of knowledge representation, more traditional symbolic logic-based approaches, as we've done a lot of work on planning, logics, and so on. But the last 10 years or so, we've been doing much more work towards machine learning. And what's really interesting, of course, is this intersection or the combination of these different techniques. We've also working quite a lot on multi-agent systems, both on something called combinatorial assignment, but also on multi-agent reinforcement learning and task allocation and so on. So what I want to talk a little bit more about in detail are actually there's 5 things I will be presenting, but the kind of main parts when it comes to this learning and reasoning about the trajectories. We have learning generative models based on trajectory data. We have probabilistic logical reasoning over observed and predicted trajectories. And we have privacy-preserving synthetic trajectory data generation. And then I will be talking a little bit about this utilitarian combinatorial assignment, and extremely briefly about our work on multi-agent reinforcement learning. So one of the things that we've been doing a lot of work over the years is this: how can we recognize different types of motion or other activities on the ground? So one of the applications of our UAVs, of course, was to fly over traffic and try to understand what's going on in the area. So it's very much about understanding the kind of motion or the activities that the vehicles are doing. So one of the works actually that Matthias Tiger has been doing, who's defending his thesis on December the 8th, is on motion pattern recognition. So basically the general idea here is to, we have a tracker, so you have some, for example, a camera-based system that produces a video stream, and then in this video stream you recognize objects, and then you track these objects over time through the images or the video, and then you generate trajectories of where so you geolocate them, so you basically know where the camera is looking, so you can compute where are these vehicles or objects on the ground. So then we generate these trajectories of motion for these vehicles. Of course, if you're so lucky that you have a GPS data, that of course simplifies things, then you don't need to do this kind of tracking and geolocation yourself. That's done for you. And then from these trajectories, we want to learn motion patterns. So what are common ways that these objects move, so that we can then use these motion patterns to do different tasks. For example, anomaly detection. So you detect, is it following this expected pattern or is it deviating from it? You can also do multi-class classification. So basically, which of these motion patterns does a particular motion match to? We can predict how a vehicle will continue to move, so predict the kind of future movements. We can also predict sequences of these motion patterns, so working at the higher abstraction level. We can also do temporal alignment of trajectories, so basically scaling, and I mean, you, for example, dynamic time warping, where you take two trajectories and then try to align these. So these are then some of the things we've been doing. So one kind of prototypical example of the things that we wanted to do was that given trajectory data such as this, so each line here is one trajectory. The color corresponds to speed. So basically, you have a steady speed. Are you braking or are you accelerating? And from these trajectories, we want to learn the kind of common motion patterns that these vehicles taking. So in this case, do you have all the vehicles kind of entering the crossing, in this case from the right towards the left, and they all kind of share a common way of approaching the intersection. Then at some point they start to deviate. Either they brake and then they turn and then they accelerate, or they kind of go straight through the intersection, and in this case they don't need to slow down. So basically the way we model this is with Gaussian processes. So that's a parametric model. So we learn, or non-parametric model. So we learn how to represent these motions on a very high level dynamic detail. And then we have these connections between these different motion patterns, which are these white circles, which are then the nodes in our network. And each of these motion patterns is then an edge in the network connecting two of these nodes. So this is then what we actually learn. What we would like to do is, of course, to be able to generalize this and understand the kind of semantics. What does these different things mean? But that's future work. So to continue on this example, so here we have taken one of our UAVs, we have flown it in a grid-like pattern indoors, just to generate some trajectory data and see that our model can learn to build incrementally a model of the movement. So in this case, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different motion primitives and 7 change points. And then if we get a new trajectory, so the blue one here, we can see that we are following the trajectory, or I mean, we are matching the first motion primitive here. Then we switch, so we take a right turn, we follow this pattern, we do a left turn, and we follow this pattern here. And then, but then we kind of continue. So here we have a stretch of the trajectory, which is not explained by the current model. And then we see that it kind of goes back into the existing model. And then what we do is that we incrementally update the model of the environment based on this new observation. So what we do is that we now need to add one more motion primitive, namely this new part here. We also need to split up this long motion primitive into 2, and then connect the 3 of them here. So it means that for each trajectory that we observe, we can then update the model if it does not explain the data that we have seen. So just to give a bit more detail, so what we get is actually a multi-class classifier. So each of the colors here correspond to one of the motion primitives. So then we can see that we have like the most likely motion primitive, and then when we enter towards this intersection, we see that the likelihood of the purple one goes down and the likelihood of the orange one goes up, and at some point it crosses, and then it kind of takes over until we reach the next point. And here we see that we actually have 3 different activities, so that's why we get this green as well, and just like we have a blue here as well, corresponding to going straight ahead in that crossing. And then we can also see that we have this particular area here after 0.5 where no activity or no known activity can explain the behavior, and that's then how we identify that we need to update our model and to identify where we need to add a new motion primitive. So this just shows how it works in a little bit more detail. If we go in one more level of detail further, we're actually modeling this as a 2-dimensional flow field. So we can represent both the direction, so kind of the direction of the motion in 2 dimensions, so that we can represent this kind of turnings and so on and so forth. And this is then the actual representation being used by the system. Yeah, we also need to maintain an inverse mapping. So basically, from an observation, we can detect where in this motion pattern we are. So we can both kind of from observations detect where we are, but also kind of follow and predict where we're likely going to continue in the future. So I think this is a pretty nice combination of a very detailed continuous representation in form of Gaussian processes, together with this more discrete symbolic representation of the motion primitives and how they are connected. And you can also have transition probabilities, so they can represent how likely it is to continue in different directions. So this was the first example. The second example is probabilistic logical reasoning over observed and predicted trajectories. So one of the things I did for this UAV project that I mentioned in the beginning was that I was responsible for doing execution monitoring, and the whole idea is that normally what you do is that you have a model of the system, and then you verify that this model has certain safety and liveness conditions. These are often expressed using temporal logics. So what we did was that instead of, because the problem is it's very difficult to provide accurate models of the system. And of course, it's even more difficult to have a model of the environment. So therefore, we don't believe that it's really possible to do this kind of detailed models of the system, but rather what we did was that we monitored a particular execution of the system. So what we were monitoring was that every time the system was actually executing, running a mission, then we could verify that it didn't violate any of the safety and liveness conditions for this particular run, which is then computationally a much simpler problem. And we don't need to have a model of the system, but rather we monitor the observed behavior of the system. However, that means that we are able to detect if the system is violating some of these constraints, which of course is important, and that allows you to take evasive maneuvers or doing some kind of emergency landing or whatever you want to do. But it would be even more, or actually, I mean, it would be much more useful if you can also monitor the likely future behavior of the system. So what we did in this work was that we extended this from more traditional kind of Boolean logic into a stochastic logic, so that we can explicitly represent uncertainty. We also included the possibility to include generative models of likely future behavior. And then you can do reasonings over predictions of what the system is likely to do in the future. So then you can not only monitor the observed past, but also the likely future. So then you can detect if things looks like they're going in the wrong direction. And also this was integrated in an approach to reasoning that we called stream reasoning. So actually it was one of the major parts of my PhD thesis, and the image to the right is actually the cover of my PhD thesis. So one of the things that we discovered was that when you're working with these autonomous systems, they collect a lot of different information. So basically, there's almost infinite amount of information that you could collect while flying and doing things. But of course, you don't really have the processing power to store everything and then process it afterwards. So what we wanted to do was to go from persistent data, where you store all the data and then you ask queries to the data in traditional database or knowledge base, and turn it around so that you start by asking the query. So what is the things that you want to find out? And then you collect the particular information that you need in order to answer the query. So in this way, we are turning things kind of upside down. So we start by the query, and then we collect the data, and then we try to, and then with the purpose of either answering the query, and if it's a logical query, then of course it's about evaluating it to true or false. And then we call stream reasoning, that when we say stream reasoning, what we mean is the incremental reasoning over streaming information. So as soon as we get new information, we want to update our queries or our logical formulas, so that as soon as possible, we're able to answer the query or to compute the end result of this, evaluate this temporal logical formula, for example. And then this is very much related to this 4 V's of big data. So, this was IBM's slogan for big data a number of years back, where they talk about these large volumes of data. They talk about high speed of data, the high velocity of data. They talk about data having many different forms. So it has a large variety, or many different varieties. And also the uncertainty of the data, or the veracity, how true or valid is the information, is also important. And our focus here is really on the velocity, variety, and veracity. We haven't really focused on scaling this up to very large volumes of data, because that requires kind of different types of techniques. And one thing that's very important for us was also this constantly changing circumstances. So we don't believe that, especially if you're building an AI system or autonomous systems in general, that you cannot specify in advance exactly what's going to do, but rather the system itself needs to be able to configure it and reconfigure it at runtime so that it's appropriately adapted to the particular task at hand. And this requires this to deal with all of these while within this kind of constantly changing circumstances. So the type of stream reasoning that we mainly been working with is what we call spatial temporal stream reasoning. So we're using metric temporal logic, which is a traditional temporal logic, where you also can have metric constraints. The benefit of this logic is that, first of all, it's quite expressive, but also it's quite natural for us humans to kind of write and interpret these formulas, while they still can capture very complex phenomena. And I will not go through this example in detail, but it's basically monitoring the power usage of a UAV. The challenge is that the semantics of these formulas are defined over infinite state sequences, which means that normally you need a whole infinite state sequence in order to determine whether a particular formula is true or false. So what we did was that we used a different technique called progression, which then allows us to take one state and compute a new formula such that if the new formula holds over the rest of the state sequence, the original formula holds over the whole state sequence. So basically a way for us to do partial evaluation, one state at a time, of these temporal logical formulas until they collapse onto true or false, and then we're done, or we will just keep on going. So this will allow us then to determine if the prefix of this infinite state sequence we have seen is sufficient to determine the truth value of the formula. So that was the starting point, and then we extended it with this probabilistic logic. So what we did was that, this was the way it worked before. So you can say something like, the altitude of the UAV has always to be above 3 meters because we're not allowed to fly at a very low altitude. What we can do now is that we can say that the probability that we're above 3 meters should be at least 99% or 0.99. And in this case, it would be false because we see that the probability mass of this probability distribution, so this is the probability distribution of the actual height. So we don't know, we don't know exactly what height we are at, but we can see that we have sufficient probability mass that is below 3 meters so that this particular statement here is false. And then we also added this that you can tell at what time point you should do the reasoning and for what time point you should do the reasoning. So you can say, for example, that 2 time units from now, the altitude should be above 3 meters with 0.99 likelihood. So then we can also talk about future events or past events. So the way that it works in a little bit more technical detail is that we have 3 levels of features. We have the actual observation itself, and we have the estimated features. So for example, we're doing state estimation. So you can use a Kalman filter, whatever particle filter, whatever method you want, target tracking. And then you get an estimated feature. So this is the estimated altitude, at the current point, at the current time. But we can also then talk about future and past predictions. So in the diagram here, we can see the orange, these are the states that we observe. And then based on this current observations and a current state, we can now estimate our next state, or maybe we should say the estimated previous state together with observed current state. Then we can estimate our current state. But we can also do the predictions, which are then the red ones. We can either predict things backwards or we can predict things forwards. So that gives us a lot of flexibility. And when we talk, so we can basically refer to each of these states in this two-dimensional grid in our formulas. And why is this relevant? Well, it gives us flexibility and expressive power. So for example, we can express probabilistic statement. So what is the probability of a collision, for example? In this case, what's the probability that we are in a no-fly zone? So even though we have uncertainty in our observed and estimated positions, we still can deal with this in our logical framework. We can do anticipatory reasoning, meaning that we can reason over predictions or likely futures. So then we can say, what's the probability that we are likely to collide with an object in the close future? And then, of course, we want to avoid future collisions. And then one of the things I actually find the most interesting is this introspective capability, where we can reason about our own predictions. So we can, for example, say that what's the probability that the predicted position, say that we predict where we would be five time units from now, we can compare that prediction to the actual observations 5 time units later, and then we can compare whether our predictions and our observations are congruent. So, I mean, if the distance between them is small, then we have good predictions. If the distance is far large, then we have bad predictions. So then we can actually do introspective monitoring of our own predictions, our own sensors, our own controllers, and so on and so forth. So it's actually quite powerful. As I already mentioned, one of the things we're doing is to do this for making sure that we have safe autonomous systems through, for example, introspective motion planning and control. So we can learn models of normal behavior, and then we can detect if we're deviating from these. So we can monitor the execution relative to these models. And if they are deviating from these models, then they're not behaving normally. We can also have models with explicit uncertainty quantification, so that we know within what bounds we will move, so that when we do the motion planning, we can add the fact that we don't have exact information, but still we can guarantee that we act safely within these boundaries. And then, of course, we can also monitor the models with respect to the execution during deployment. So, as I said, we're doing this introspective monitoring so that we can actually verify or at least detect that the models we use are appropriate and capture the things we want. And then we have integrated this into a lattice-based motion planning framework. So actually, everything is integrated, so we have a very nice AI robotics stack and simulation environment. So we're using ROS as the kind of integration framework, and we're also using Arbis and Octomap and this Gazebo. So basically, the tools built into ROS, and then we have integrated our different technologies into that. And of course, or not of course, but one other application is motion planning, 3D exploration. So basically how we explore a 3D environment, but also coverage path planning. So for example, in coverage path planning, the question is, assuming that you have a cleaning robot, such as the red one in the middle, and now you want to drive that around in, say, for example, a parking garage, so that you sweep all the floors, all the floors on all the different levels, and then we can actually generate these paths with very high accuracy. So we have some papers about that. And of course, we have a bunch of different papers. So if you're interested, you can read more about them in those. So that was the second topic. The third topic is privacy-preserving synthetic data generation. So here what we're interested in is to, in many cases, we have data that might be sensitive. For example, one project we had movement data of people move around from a telecom provider. It could also be health data. So you have patient data. And so the problem, the thing with this data is that it's sensitive and you're not allowed to do everything, and you might not want to do it even if you were allowed. So the whole challenge or the whole question here is, how do we take this sensitive data? Can we learn generative models of this sensitive data so that we can use these generative models to generate synthetic, non-sensitive data that preserves the relevant properties? So the whole idea here is that you can do this training of these generative models on the sensitive data in a closed environment. And the only thing that you export from this closed environment is this synthetic data sets. So that if you just have the synthetic data set, you're not able to re-identify or identify the particular individuals in the original data. But if you use the synthetic data on downstream tasks, such as a classifier or whatever you want to build with this predictor, you should get the same, or at least a similar performance accuracy on this synthetic data as you got on the original data. Then we have succeeded. So this is one research area that we've been working on for some time. And one of the results, or the kind of, maybe I should say ongoing, so it's not published yet, is that we're working with synthetic health data. So as I said, health data is one of those topics where there is a lot of sensitive data. And the things that we want to do is to deal with both the fact that different populations might have different coverage. So we want to make the data more representative by dealing with rescaling the density of different subgroups. And we also want to reduce the bias in this data. So we use this score-based weight samplings to respect the different subgroups. And then we use mutual information constrained GANs to remove the connection between sensitive attributes. So basically, there might be certain attributes that we're not allowed to base our predictions on. So, for example, sex or religion or these kind of things. And then we can use this mutual information measure to make sure that the different variables are disconnected so that there is no dependence between them. And then we can use a GAN-based architecture, Generative Adversarial Network, to train and learn these generative models from which we then generate this synthetic data. So yeah, it's a bit complex, but the overall idea is that we have a generator, just like you do in normal GANs, that is then learning to generate samples from the same distribution. And you also want to be able to determine the class. We also have a classifier so that they can then classify inputs. And the purpose here is that in many cases, when it comes to this healthcare data, it's incomplete, which means that we need to fill in the missing gaps. And that we do through this classifier, so that we can fill in missing data by looking at the other data. So we can also do that. And then we have the discriminator, which again is a traditional part of the GAN, which is then trying to determine whether the generated sample is a fake sample, or if it's, the data that it gets, is it a generated sample or is it a real observed example? And then we need to have this mutual information and this density estimation to compensate for these different groups and to disconnect the sensitive attributes from the end results. So when you train the system, you get something that's significantly better than the existing state-of-the-art systems, namely HealthGAN and FairGAN. So here we're comparing our methods on 2 downstream tasks on using a linear regression based model or a random forest to classify the objects, or sorry, yeah, to either determine the intensive care unit mortality and the time it takes to leave the hospital, and then of course so we have a number of different kind of things we want to do with this data. So we can see that the real data, of course, that gets the highest results. But we actually get very close, so it's like slightly less accurate compared to the original data, and also pretty so that we are significantly better than the health GAN. Then there are some cases where it's kind of comparable, and then for other tasks we are better. So the whole point here is that we are at least as good as the state of the art. But then we can also see that we are much more fair. So we can see that in this case, it's the fairness gap between whites and black patients. So here we get significantly better results than the health GAN and fair GAN, except for one case where we get slightly worse. But it's basically so small errors that it's negligible. If we then do this kind of group analysis, we can see that our system, so health GAN is the quarter or third up here. So we see that it doesn't manage to get a fair distribution, but it either underrepresented or overrepresented in different areas. So we see that our kind of basic version also has the same problem. But if we're doing this, taking this density function estimation into consideration, we can recalibrate the different subgroups so that we actually get a fair representation of all the different subgroups. So this shows that we're able to compensate for both the bias and the representativeness of the data while maintaining or improving on the accuracy compared to the state-of-the-art methods. So this is one concrete example or using that. And I should say that the data that we look at here is time series data. So this health data is usually a time series. So that's why it's also a trajectory data. So what I presented here in this part was this learning generative models based on trajectory data. I talked about probabilistic logical reasoning of observed and predicted trajectories, and I talked about privacy-preserving synthetic data generation. And then I have 2 more topics that we're covering in my group. So the first one is this multi-objective, multi-agent reinforcement learning. So here the whole point is that what we want to do is that we want to use multi-agent reinforcement learning to learn agent behavior, but we want to apply this to pilot training. So he's an industrial student at Saab, which is an aircraft manufacturer, and they also do training simulations for pilots. So the idea here is that how can we generate appropriately, sophisticated either partners or opponents to you in these flight simulators in order to optimize the pilot training. And therefore, he's looking into multi-objective, multi-agent reinforcement learning. So the idea is that instead of learning a particular objective function, it's actually learning a class or a family of related objective functions so that the person who is in charge of running the training simulation can adapt the agent at runtime by basically reweighting how it takes these different objectives into account. So this then provides a lot of flexibility to the trainers running these training simulations. This is a bit outdated. We have some nice results after this as well. And then the final thing I want to talk about is the problem of combinatorial assignment, and more specifically the utilitarian combinatorial assignment, which we have been working on. So the problem that we're interested in is that assume that we have a set of, for example, agents, could be other things, and a set of things or tasks that we want to accomplish. And now the question is, how do we form teams of these agents and allocate these teams to tasks so that all the tasks are done optimally? This has traditionally been solved in 2 steps. So the first part is to generate the teams or form the teams, and that's called the coalition structure generation problem. And the second problem is the assignment problem. And these problems are both NP-hard problems. So of course, when we combine them and solve them jointly, it becomes even harder. So it's also NP-hard. Actually, we have proved that this problem cannot be approximated, so it's non-approximable within to a constant bounded difference from the optimal value. So it is truly very challenging from a computational perspective. And then we can have 2 different, or I mean many different ways of how to do this allocation, the assignment. So the work that we have been, where the focus of us has been on utilitarian. So we basically want to maximize the sum of the utilities of all the different combinations. But we can also have a more egalitarian perspective, where we want to minimize the difference between these, so that we can have more equal distribution of resources, or distribution of utilities. And this is actually an extremely general problem. So it generalizes a wide range of different problems. Of course, the assignment problem, which is one of the special cases, but also multiple vehicle routing. So basically, for example, here is about how to route different taxis in a city, but also multi-sensor, multi-target tracking. So how to, given that you have multiple sensors observing these targets, how do you track them? And the winner determination problem in combinatorial auctions. So that given these bids, these combinatorial bids, select who should be awarded the different items. And then team formation, of course, because that's a special case again. And course allocation is another one of the special cases. So it's an extremely generic problem. And here we have state-of-the-art exact methods. We have state-of-the-art heuristic methods. And we also have, now we're currently looking into how can we use machine learning to learn heuristics for better solving this problem. So basically trying to predict, given a partial assignment, how good can this assignment be when it's fully assigned. And then we're using that as part of a Monte Carlo search method, and then we can be able to solve even larger cases. And this has also been used in a commercial setting, so it's actually been used in a commercial game, Europa Universalis 4, which is then a real-time strategy game, and there it's being used by the computer player to determine what units to form armies from, and which country or region that this army is then going to attack. So it's about how to select what units to include and what to do with this kind of army of different units. So it's also a commercial success. And of course, we have a bunch of different references if you're interested in more details. So these were then 5 particular topics that we are currently working on. I should say that we very recently got a new project approved for multi-drone route planning in I forgot the name, but so when in controlled airspace, so basically the question is that you have a air authority which is covering or responsible for certain part of the airspace, and now it needs to deal with all the routes for these different drones or other flying objects. And now you want to introduce either new drones into this airspace, and then you need to compute what is the optimal route for this new drone. Or you might add constraints. So, for example, add a no-fly zone, or there might be communication constraints that you always need to have certain quality of communication. And therefore, that might degrade. So then you need to reroute the drones and need to recompute many different routes given these new constraints, and so on and so forth. So here we're opening up for new research, and this will be done in collaboration with Ericsson Research in Brazil. So this will have a very clear Brazilian connection to this project. If we take one step back and see what is the kind of more like long-term or general things that we are interested in, we're very much interested in this kind of learning from how humans think, and of course related to computational thinking. And here it seems like people have kind of two main different ways of approaching thinking. So we have what's called the system 2 or the slow system, which then corresponds to, I usually use this kind of prototypical analytical thinking, where we have a very explicit problem and we need to find a very explicit set of action or steps in order to solve this particular problem. And basically that's what we do most of our days. We provide analytical solutions to this kind of analytical problems, often using different forms of logical reasoning. And I would argue kind of the traditional symbolic AI method have been extremely successful at this type of problem solving. But we also have the other type of problem solving, which is what we call intuition. So it's kind of unconscious, effortless, and automatic. And we have very little insight into how it actually works. And as I said, intuition is one of the prototypical examples where given a question or giving a problem, we often intuitively feel what is the right answer or what is the right way of solving this problem. And in many cases it is, but also it can also be wrong. So there is no real guarantees here. And this then corresponds to the kind of modern data-driven machine learning-based approaches, where we're able to, using machine learning, learn complex models that are very capable of very efficiently answering questions or detecting objects or doing all kinds of things, where it's most of the time it's correct, but then sometimes it's very incorrect. And the question here then becomes, how do we combine these two different types of approaches in a systematic and meaningful way, so we can build this kind of hybrid AI systems combining data-driven machine learning with this more knowledge-based and more importantly analytical solutions, where we can actually prove properties and have analytical guarantees around the quality of these systems and how long it will take to compute and converge and all these things. So this is one major research trend, how to achieve that. So in some sense that covers the left part of this image. So the second part, which I think is very important, is that I think we need to move beyond the kind of traditional correlation-based approaches, where we're learning how things covariate, into learning more causal representations and causal structures. So we actually know the direction where the kind of arrow goes, so that if we want to change the future or want to influence the behavior of a system, we know what to actually change in order to achieve this change in environment. So what we need to do is then to learn these causal models based on both data and these knowledge assumptions, And then we can use these causal models for reasoning in order to explain things that we have observed or to predict things that are potentially going to happen in the future. So this also gives kind of a high-level future direction of some of the research. So this was an overview of some of the main activities that I'm doing in my research lab, the Reasoning and Learning Lab, where we're very much interested in this kind of intersections between these different areas, reasoning, learning, and multi-agent systems. Before I end, I want to say a little bit more, general things. I think Linköping University is quite interesting in the sense that we cover all aspects of AI in one university. So of course, at least, many universities, if not all universities, of course, have some AI competence. I think the difference here is that we usually have, for each of these major sub areas of AI, we usually have research groups, not individual researchers, but actually research groups. And in some cases, we have several extremely successful research groups, for example, in computer vision, where we have at least three very good research groups on that. That's just one example. And of course, we also see that AI as a topic or a subject is broadening. So it's going beyond this kind of technical core and towards the humanities and social sciences, which I think is very interesting and very good progress, so to speak. I also think that in order to be able to address these major challenges, we really need to look at the larger ecosystems that many of these research challenges and other challenges are beyond what any particular research group can do by themselves, but rather we need to find and develop these ecosystems. And I think we're actually starting to get a pretty good ecosystem, at least in Sweden. So in Sweden, we have a very large research program called the Wallenberg AI Autonomous Systems and Software Program. So this is a basic research program, Sweden's largest research program. So we currently have a budget of about 600 million euros, or more than 6 billion Swedish kroners. And you can divide it by 2, and then you get the amount in reals, so about 3 billion reals in budget for 15 years. So it's also a very long-term program. And here the goal is to do the basic research today in order for industry to be competitive in the future. So it's very much about basic research, but where the basic research should be relevant and valuable to industry. We have 2 sister programs, WASP-HS, which is about humanities and society. So this is where we do this kind of ethical, legal, societal, economical, and so on research, studying AI or autonomous systems as a kind of a subject. We also have a program called WASP-Ed about educational development, and this program I'm the program director for. And here we really want to accelerate and scale up and scale out AI education in Sweden. We also have an initiative called AI Competence of Sweden, where we are looking at how can we educate professionals about AI, both in the public and the private sector. We have an initiative called AI Sweden. It would used to be called AI Innovation of Sweden, with the goal of accelerating the use of AI both in the public and the private sectors. It's very much on the application side of things. And then we have this Taylor network that I'm coordinating on the foundation, scientific foundations for trustworthy AI. And we're also starting to get a pretty good ecosystem in Europe, including many different actors. And of course, Linköping University is involved in all of these different initiatives. If you're interested in education, I'm super interested in AI education. Well, in education in general, also how can we teach kids about programming, or more generally about computational thinking. So I've been doing a lot of work on computational thinking, basically bringing the concept to Sweden and getting it into the Swedish national curriculum a number of years back. And now we're very much looking into how can we, as I said, significantly scale up the national education capacity when it comes to AI, but also scaling out education to other disciplines and professions beyond this kind of technical core, and how can we do this data-driven education and pedagogical transformation. So there's a lot of interesting things going on when it comes to education. And as kind of a closing point here, as I said, I've been working a lot on this trustworthy AI, and I think one of the things that, I mean, actually it's also related to the work that I've been doing, but how, I mean, I think one of the major kind of promises or potential here is how can we use these systems to learn, or I mean, how to make better human decisions. And I really think that's one of the kind of key overall objectives here, is that how can we enable and help people making better decisions than they can do today with the kind of existing methods. But here I think we also have a challenge, in namely that when we start to analyze human decision making, we may realize that actually we are not as good at decision making as we wish or that we thought we were. One concrete example here is from France. So France made basically all their legal cases and so on available digitally a number of years back. And of course, researchers start to do studies on how French judges make decisions. And I think they were studying this asylum cases. And there they came to the conclusion that it mattered more which lawyer you got than the actual circumstances of your particular case. And of course, this was not the desired outcome or the expected behavior. But the interesting thing is what happens next. So, of course, these researchers go to the French Bar Association and ask, oh, are you interested in this? Can we work together on this result somehow? And say, no, we're not interested. And then media finds out, and of course, it becomes a big fuss. And then what happens? Well, in this case, they actually created a law making it illegal to study how French judges make decisions. So basically, making it illegal to do that kind of study again. So instead of actually fixing the problem or improving the way that these humans were making their decisions, they rather make it illegal to do this study. And I really think this is probably quite symptomatic of what we can expect in many cases. But I really hope that, of course, the applications we do will be different. I think I've said concluding several times, but I think now it's actually very close to concluding, is to look at, if we go back to games, I mean, games has been one of those areas where AI has been used for a long time. I think the first case was probably checkers was in 1959, I believe, when Arthur Samuels built a checkers playing program that was beating him. So his argument was that since I built a computer program that was significantly better than myself, it means that I could not have kind of programmed the knowledge of how to play the game into the system, because I don't know it, obviously, but rather the system itself learned, so it used an early form of reinforcement learning to learn how to play the game so that it could beat its creator. But we can also take chess as another example. So, I mean, chess is an example of a game where we humans don't have a chance against the computer, and we haven't had a chance against the computer at least since 1997, when Garry Kasparov lost against IBM Deep Blue. For most of us, of course, the computers have been better than us for a long time, but even for the best, they have been better for the last 25 years. But what's interesting is that what happened with Garry Kasparov after he lost. Of course, first of all, he was super angry and frustrated by the fact that he lost. But then he realized, I probably will not be able to beat. So instead, he kind of joined the computer and started to develop these computer playing programs. and now I think he made a fortune from these computer playing programs. But he also had a competition where humans, together with these chess playing computers or chess playing computer programs, were playing in teams against both humans and the kind of purely computer playing programs. And what he found was that these teams, these centaurs or these AI human teams, were better than both the best humans and the best computer programs. So it's really the case that it's not a question of either AI or humans, but really AI and humans together. And that's how you really make success. At the same time, it requires a different skill to play chess with a computer program compared to playing chess on your own, which means that we really need to invest as much in competence development as we're investing in buying the kind of hardware and software and the kind of infrastructure and so on. And secondly, we need to change the way that we work in order to take advantage and leverage these tools and really use them to our best advantage. So I really believe that the future belongs to AI and humans together. Thank you very much.
Thank you so much, Fred, for your very interesting presentation. I think it was, for me, it was very, very exciting, and it brought me very many ideas. I will first ask the audience if someone have any questions. You can talk, Rafael.
Flavia?
Hello, Frederick. Thank you for your presentation. It was actually really interesting. And I would like to know about your interest in optimization. You said before about routing and assignment optimization. And I enjoy my master's in mathematical optimization, mainly interest in operation research. And I would like to know what you have about this knowledge, this field, if you have any interest about it.
Yes, I mean, I do think there's a lot of connections. That I think the distance between kind of combinatorial optimization and the work that we're doing is very, relatively short. And actually, we are also collaborating with the math department here, Elina Rönnberg, who is also involved with this Saab. They have some collaboration there. So I think there's actually, we had a workshop like a month ago on hybrid AI where data meet models. And one of the topics was really on combinatorial optimization and machine learning. So one of the really interesting areas today is how can we use machine learning in different ways to scale up and speed up combinatorial optimization. And this example I gave on this combinatorial assignment problem is an example of combinatorial optimization problem where we can use machine learning to really speed it up. I think there is also interest in many real-world constraint problems or optimization problems are under-specified. So the question is, can we learn what the actual constraints are so that we can solve the problem and so on. So I think there is a lot of interest in this intersection between optimization and learning. And of course, optimization is what you use for the learning. So many game theoretic problems and machine learning problems are kind of compiled down into optimization problems that you then solve using an optimizer of some sort. And that the outcome of that will be your system. So definitely, I think there's a lot of interesting connections there.
Yeah, thank you.
Mario, did you raise your hand to talk?
Yes. Hi, Frederick. Thanks for the nice talk. And it's a very interesting project. So I'm more in the logical part, so I'm more interested in temporal reasoning, spatial reasoning. I've been working with some temporal logic for analyzing social networks and so on. So if you could make available the reference, some reference for working in the temporal logic, I would be grateful to read it. And
Yep. I mean, I can share the presentation. I mean,
okay.
my papers are also available on my website, so everything should be accessible. And if there's something that's not available, just let me know and I will send you the papers.
Okay. Thanks.
Anyone else? Well, there are some questions that I was wondering, how did you work? I've been working more with machine learning and data stream learning. I mean, the part of machine learning, I'm focused on data stream learning, data stream, aware of this kind of work that Albert Buffet and John Gama have been doing the last 2 years. So there are some questions that I was wondering when you were presenting, because it seems to me that the reinforcement learning paradigm is the one that you have been working on much more. And but there was a slide that you showed that you were discussing the use of Bayesian models for. I think that it was in the reasoning part. Could you discuss a little bit more of which algorithms? It's all the generative models, or do you use any data stream mining techniques? Are you aware of the work that Albert Buffet and João Gama and so on have been doing? It's more, it's a bit big rhetorical question maybe, but it's good to discuss.
So, I mean, I think the short answer is we have not really done anything on data stream mining. We are more the kind of the properties that you want to verify that a stream has been manually written. So, for example, these kind of safety constraints and so on, normally written by the designer of the system. So these are the things we want the system these are the properties we want the system to have. And now it's more a question of verifying or checking whether they have it or not. So it's not about discovering new patterns. So therefore, I have not really followed the data stream mining literature. I reviewed some papers, but that's not an area where we have been keeping track. I should also say that most of this work on stream reasoning, we haven't done that much the last 2-3 years. Since the PhD student I had was working on it, Daniel Deleng, he finished. So currently we're not explicitly working on that anymore. And when it comes to reinforcement learning, so I do think there is a lot of connections between this kind of stream-based systems, these incremental systems and so on, and reinforcement learning. But again, we haven't really pursued that. And what I think is the interesting part there is that the stream reasoning and kind of trying to understand what's happening in the world around it's very much more understanding, and then reinforcement learning is actually acting and changing, so that you kind of get this duality. In some sense, it's about understanding what the world is like now, and then based on that you need to make a decision, and then when you do the decision or you do act upon this decision, you change the world, and then you get the kind of feedback loop and so on. So then you can try to control the world so that it generates the data that you wish to see. So yes, I do think there is interesting connections between this kind of stream reasoning and reinforcement learning, but it's not something we have had the opportunity to pursue yet.
Yeah, I think that one of our main problems that we face when we are working on data stream mining is to label the data. I had a PhD student with Vitebo. He finished it this year. He defended his thesis this year. He's here. Leandro is here. And he worked with human activity recognition. And we tried to explore data stream mining, but one of the most difficult part was to label the data. Because when you are working on data stream mining and data stream learning, if you are on the supervised mode, you need to label your data continuously. So this is a big issue. And we didn't realize yet how to solve this. Is a big challenge yet. But even if we are in the smart cities context that I told to you in our last talk, that I'm very interested in this kind of applications, there are many situations where data stream learning is applicable, but sometimes it's very difficult to collect the data. So I think that you have a very interesting equipment, and it may be costly to have them. So I think that there is a probability to start working with that. And this can be a very interesting point of connection to think about, to simulate some situations. And only when you show it, the robot for cleaning the spaces. I understood that when you said that when you have GPS, you don't need all of this stuff. But there are many problems that we also worked on, that it was predicting bus time traveling and so on. These are, you have the GPS data, but it's very difficult to predict them correctly. And there are some latency or delay problems in these scenarios. So I'm very interested in this kind of problems too. So do you have any, could you share what you think about when you have GPS data? What is the main difference with you have done?
So I mean, from our point of view, I mean, we assume that we have some position information available, and that this position information has some uncertainty representation. And of course, that depending on how you get the kind of position, if you use GPS, then you have certain uncertainty regions. If you use the more this vision-based approaches, then you get other uncertainty regions, so on. So we treat it more as that is depending on the method, we get different amount of uncertainty in the observations, and then we treat that within the system. But I think there was very interesting this comment about the difficulty of labeling data, because one problem which we have started to look into, we don't have any results, is in self-supervised learning or semi-self-supervised learning. And actually, I think there's very interesting in this case, because you might be able to somehow, you might not know exactly how the data looks like, but you can have other things. I mean, a concrete example would be that you can have a static camera looking at a particular view. So I mean, I don't know, you're looking out the window at a parking place. And then, of course, you don't know exactly what's in the image, but you know the things that are not changing, and you know the things that are changing. And in some sense, you want to learn to detect the background for the foreground, or the static from the dynamic things. And in some sense, it's all about the system that you have trained so far, you can use that to predict what is expected. And in some sense, you get the ground truth from, I mean, if something moves, then it's apparently something movable. If it doesn't move, then it might be something that's static. And then use kind of invariants or things that doesn't change in the environment as a way of learning. So you don't need to do all this labeling. Of course, you can also do things like autoencoders, so basically learning how to represent these different events. And then hopefully you can learn a representation such that the kind of metrics on this representation, which you've learned completely without any labeling, can be used to at least differentiate and say that, oh, this concept is far away from this one, or this close to this, and so on. So I think there are a number of things one can do, even if you do not have the labels. And I would say this whole area of self-supervised learning or semi-self-supervised learning is really interesting, and I think probably relevant in cases like yours.
Oh, interesting. I have a more specific question. When you showed the learning generative models, you had the colored dots or colored nodes between two or more white nodes. So I was wondering, you told us that each one of these dots could be a neuron or so on. I couldn't really understand how did you represent that when we think about computer, or what are them?
Let me.
It was in the beginning of your presentation.
Yeah, I'm just opening it. This one? What's this one with the
Yes, this one. What
Yeah.
are the nodes?
So basically we have two things here. We have each of these green to red things are Gaussian processes. So Gaussian process is basically a probability distribution over functions. So basically this represents a set of different functions. Each function is one particular trajectory in this case. And then the kind of, shaded circles within is just that we have a kind of a uniform sampling of this underlying Gaussian process. But in some sense, it's the shade itself that represents the 95% confidence interval. So actually each of these, so this is one Gaussian process, this is one Gaussian process, and this is one Gaussian. So the three Gaussian processes connected in one single point here. And this is then a transition point. So this is a point where you transition from one motion primitive to another motion primitive. So that's one. And you can also see there is like very lightweight lines here. They represent kind of the particular trajectories and so on. So there is a bit more information here, but we use the Gaussian processes to represent the motion primitives, and then we connect these Gaussian processes using this transition nodes. So we get a directed graph where the edges of the graph are these Gaussian processes, and the nodes are these transitions between different motion primitives.
Okay, but do your motion process, does it considers the position in the 3D, X, Y, Z,
So
and
this
so on?
is only 2D. So this is 2D.
Yes, but when you are considering the helicopter, I think, didn't you use it in that scenario?
So I mean, the application or use case here is more you have a downward-looking camera, so you consider it as a 2D environment. I mean, it is relatively straightforward to extend to 3D, but the work that we have been doing has only been in 2D.
Okay, okay, thank you so much. I think my questions were these. Yes, Marisa?
Okay. Thank you, Professor Frederick, for your amazing presentation. A lot of exciting researchers. And from my side in particular, I'm interested in, I see possibilities in interactions in 2 points. And one of these points is about this learning models based on trajectories. I'm beginning to work with extreme weather prediction events, and maybe what I will ask you is some obvious question, but I was wondering if we can use it to learn climatical or weather trajectories from radar images, for example, to learn when an extreme weather event is coming from Rio de Janeiro, for example. And the second point is I'm very excited to receive you here in Brazil, and I would like to organize a special meeting with the Ethical and Trustworthy AI group to learn with you and your experience. I saw you received an award in AI Ethics Professional of the Year. Congratulations. And that's it.
So when it comes to this, can we predict other things? So the things we can currently do is that if we can get, for example, say a trajectory of how the weather front or the weather moves, then we can apply these methods to those directly. My guess is that you probably want to do slightly different things. So you probably want to more use the kind of ideas rather than to use the methods directly. My experience is that often there are similarities, but there are also differences, which means that it's usually quite difficult to kind of take something out of the box, but rather you always need to do a bit of adaptation in order to really be able to get it to we haven't, so we have some ideas, but actually it was when it comes to weather, my guess it is that it might be better to use more kind of say computer vision based methods. So it's kind of considering this as images and then trying to predict how these images will evolve and so on. I also think it's so actually one thing that we were interested in, we never did, was to do a kind of super resolution of weather. So in Sweden, basically they have weather stations along the railroad tracks. So it means that at some points along the railroad tracks, they have very accurate weather information. And now the question is, but now I'm in some other place in between these different weather stations. Can we kind of extrapolate what the weather likely is in this other place? And of course, to do that conditioned on the map. So basically, you had the map for the whole area as input, and then you knew the detailed weathers at a number of point locations. And now the question was, can we extrapolate or fill in the weather at all the other places that we don't have any observations? So that was so I think there are interesting things one can do, but I would probably approach them more from kind of this imaged based perspective than try to represent the kind of movements of this weather fronts and so on.
Mm-hmm. Okay, I will think better about it, because we have in Rio de Janeiro a special condition with mountains, oceans, and bays, and two bays, and we have meteorological stations, buoys, radar, and so on. But the prediction of the extreme weather conditions in the city is very unfair. We can predict good these meteorological conditions yet. So I will think better about it, and we could change ideas. Thank you very much.
I'd like to share some ideas here. I have a PhD student that she is working on how to detect anomalies in sensors networks when you have the geological geography and spatial distribution of these sensors, and we are exploring the use of Bayesian networks for this. But she's only interested when the sensor fails. In this case, I think that maybe the what Frederick said about semi-auto supervised learning or something like this could be interesting. And my student is still working on that. And one of the things that we are working on is what we observed in the past is that the Bayesian network, it is up to date after a while. So how to update that and so on. I think this is the main question of her thesis. She's developing her ideas yet. But I think that this could be an interesting way of thinking about this, because you have a huge graph on that, and you need to reason on this huge graph, I think.
Yeah, so again, we haven't done much on this kind of graph-based methods, but I do think they're, again, very interested. So we have looked into a little bit into graph neural networks, but there is so much more to do there. And I think this, as I said, these networks are very interesting to study and see how we can leverage the structure.
Yeah. When you said to us about teaching and computational thinking and so on, I have a student that is trying to work with or to propose new methods for better understanding data in high school level and so on. Open data, in the case we are interested in increasing citizenship and so on. Do you have, are you only interested in how to teach artificial intelligence for students on lower levels, on the fundamental levels of education, or are you also interested in other applications and so on?
So I would say my interest has mostly been on, I mean, I see that there is a need to kind of educate the future generations about these techniques. And so I've been more interested about what is the content, what are the things that people need to learn, not that much on the kind of pedagogical level. I mean, we have run, for example, we ran quite a large project here in Linköping where we had 70 teachers from 40 different schools. And we organized 2 times per semester, roughly, workshops for them. So we basically trained the teachers in programming and computational thinking. And then they were doing it, practicing it in their own classrooms with their own kids and so on. So we've been doing some of this teacher training. And we have also been running some of the kind of more computer, programming exercises for kids. And actually we've been using this humanoid robot, the Now robot. So had a lot of workshops for kids of different ages where they could come and play with program the robots and get them to do things. So we have done a variety of different things there. So that was not related to AI, but more, programming and similar topics.
Yeah, I think that one of the main challenging aspect on this is how to evaluate that the next generations are really acquiring the computational thinking aspects, evaluating if they are really gaining these abilities is very difficult. I have a partner. I'm not actually working on that, but we have in Brazil many Olympics in robotics and so on. So they are. We have a lot of work on that. But yes, it's still challenging in the public education in Brazil, because in Brazil, in the fundamental and high school levels, we have the public and the private schools. So the public schools yet need to be evolved. So maybe knowing more about your experience on that, we have been trying to give more teaching training for these teachers here too. We are still working on that. And I always think about what the starting of discussing artificial intelligence aspects, because they have a lot of things or thoughts about the AI will go into domain the world and so on. So I think that there are too much work to do for us in the universities around the world. I don't know if you saw something about that too.
I mean, there is. So I mean, let's address it, because you told the first thing you brought up was this: how do we know what they've learned? So actually, we have a project on programming didactics. So basically, what we are doing is studying how teachers teach programming in primary education. So the intention was that we would do a longitudinal study following kids through 3 years of school, primary education. Of course, this was made very difficult due to the pandemic, because it's very difficult for us to follow the kids. And actually, the second problem was that actually the teachers do very little. So I mean, the thing is that there's very limited actual programming education so far. But we have quite a lot of video material, so we've been doing video recordings of lectures, and actually we have the other people in my project team, they were analyzing this video last week. So we'll see what comes out of that. So we want to understand how teachers actually do it. And one thing that we have also developed is basically as an assessment tool for assessing their competence and their understanding. So we are trying to develop methods for actually assessing what people know, actually both the students and the teachers know about this subject. So we do have some results there as well on assessing competences.
Oh, this is very interesting.
It's a very big challenge to bring this to school. So, I mean, in Sweden, actually, as I said, I was involved in rewriting the Swedish national curriculum. I think it went into effect 2017, so it's like 5 years ago that programming was introduced, basically from grade 1. Different kind of content at different ages, but starting from year 1 all the way up to year 9, which is our primary education, and then we have high school, grade 10 to 12. But even now, 5 years later, I mean, the way it's being implemented leaves a lot of room for improvement, put it that way.
Yeah, here in Brazil, last year or this year, it was the law that I don't know if it's a law, but it's a kind of regulation that our Ministry of Education started, that we also have to have a computational thinking since the first year too. I'm not totally aware of what have to be taught in each year. I think this is a discussion yet here in Brazil, and maybe your material could be interesting to us if we think about how to conduct this. But I don't know if I told you, but in Brazil, maybe at most 5% of the Brazilian people speak in English. So your material could be useful for some of our students to translate and to generate this. This is a secondary maybe project that I'm very interested, but sometimes we need students for that. So it could be some fit that we could also discuss in the future.
So trying to think, because I think our material is actually in Swedish.
Oh, it's worse.
Yeah. But actually, what we have been using is a competition called Bebras. I don't know if it's also should be available also in Portuguese. So I think that's a very nice. Let's see, what can that be? Oh. Here it is. And I think it's also available in Portuguese. So this is basically, I would say it's a competition in computational thinking. But the good thing is that they have the same questions are being translated into multiple languages. So there is a extremely good, I think it's very good material to be used, and it's also translated.
Oh, very good. Thank you so much. I think that's it. I don't know if Frederick wants to give the final words to us.
No, I mean, I think it seems to be a lot of interesting connections, both when it comes to, I mean, the kind of more AI computer science, but I also find this education-related activities very interesting. So I'm more than happy to talk to people involved in more primary and secondary education. I'm just scrolling through my list here. I want to find a paper, because actually we wrote a pretty nice paper on our project, and I think it's kind of summarizes. So here it is. So this is from SIG CSE 2018, But there we described how we worked with computational thinking, basically how to spread computational thinking to every school in our city, and the lessons learned from that project.
Oh, very good. Thank you so much. Rafael, do you want to talk?
Yeah, I would like to talk about the perspective of these projects that you want to collaborate, and we like to do you like to talk about how the application process and how we would actually collaborate with this project and how we keep in touch with you and to keep the things I don't know how to explain it, but how we can do this partnership and keep contact with you and maybe apply from doctoral processing projects. Sorry.
So that's a very good question. So, I mean, this kind of, professorship that I have, it's basically mobility funding, which means that it's possible for me to come and visit and spend time in Brazil. And also I can bring people, other people with me. So it's about mobility, that particular funding that I've recently received. So kind of setting up and having these discussions, and if we're already doing kind of existing research that we can connect and so on, that's kind of within the scope there. Then there are specific mobility programs both for PhD students and for postdocs from Brazil who wants to come to Sweden, and I think actually there's a new call for that just recently. Let's see if I can find it. So if you're interested in spending time in Sweden and doing research here with us, then that's an opportunity. If you have research projects in Brazil that you want me to kind of be involved in, that could also be a possibility. I think that we had a meeting with FAPESP, so the Sao Paulo region funding, and that from what I understand, they have now set up explicit research, calls for funding research in Brazil, connected to because there are other similar professorships like I have, that they have now kind of research projects as well. So there is not a single way, so to speak, of funding actual research, but we should kind of open up the possibility and find potential both calls and connection to existing research.
Great, thank you.
I think that some words about this. Here in Brazil, FAPESP is from São Paulo state, yeah. And sometimes they open to other states, but sometimes they don't. It's only specific to researchers that are in universities and research centers in São Paulo. So we have to look into these goals to see if we can think about something, some project, and so on. What I suggest to you, Rafael, is to discuss your interest with your advisor, or he or she, I don't know, and think about the possibility. I don't know the name in English, but it's like here, for instance, Rafael has his PhD advisor, and we also he may also have an advisor in Sweden, and he passed some time with you. In Portuguese, it's called tutela. Viterbo, that is here, maybe he knows the word in English. I don't know if Marisa knows. It's like
co-advisory.
Co-advisory.
I think it's it.
And this is total possible. And one of the things that I told to Frederick, that is in Brazil, we are having struggle. We are struggling in research financing. So maybe it could be very interesting to better understand your mobility options, to see if we can send students to work with you. As I told you, I'm going to discuss with my students. I also have a student working on forgetting, right to be forgotten in machine learning, and he is specifically looking into data stream mining and how to forget in this scenario. And there are some situations that we consider that could be interesting. I don't know if you are interested in this topic too, because forgetting is a very difficult situation in machine learning, and we believe that there are some situations that this could be or will be necessary. So it's another project that I'm involved. I also asked him to stay here listening to the presentation. He's here, is Regis, and it's another possibility. So one of the things that Rafael could think about, or the other students in our PhD program, is that, well, there are some feats or some interesting ideas or some interesting problems that Frederick showed to you, to us, and not necessarily need to go there to solve your thesis issues or questions, but instead help his group to work on some gaps, some ideas, some problems, and so on. And in my understanding, that's what that are the next steps, I think.
Great for the answer, Flavia. Thank you.
Thank you, Rafael. I think we are reaching the end of our meeting. Frederick, very, very thankful. We are very, very thankful for your presentation, your good presentation. As I told you, there are many interesting problems that you were working on. I think that we can find some fits. And I hope I'm waiting for your answer when, if you are really coming next April or not, if you will be able to do it. And that's it. Thank you so much. Thank you all for the audience here with us.
Yes. No, I mean, regarding the visit, I mean, I have planned it in my calendar, so I expect I will be coming. So that is the expectation, and so it's so yeah. But of course, I will get back when before I book the tickets and so on. And I'm sure there are a lot of interesting connections. I sense, I mean, the things that you presented and other people have presented seems to be a lot of potential here. So I look forward to it.
Yes. Thank you so much, Frederick. We stay in touch. I'm going to send to all of you the link to YouTube of the Frederick presentation and his email. May I send your email? Because if someone needs to ask something, that's it. Thank you so much again. I'm going to stop recording.
Thank you. Bye-bye. Have a nice day.
Thank you.
Bye.
Bye-bye.